SISSA IFPU joint seminar. Uh, Today we have with us Antoine Lehébel. Antoine is currently a postdoc researcher at the Instituto Superior Técnico de Lisboa. And during the last years, he's been dedicated to the study of black holes and neutron stars in modified theories of gravity. Antoine got his PhD at the Université Paris-Sud, Université Paris-Saclay, under the supervision of Professor Christos Karmousis. And afterwards, he moved for a postdoc at the University of Nottingham, working with Professor Thomas Sotiriou. And now, since 2020, he moved to Lisbon for his second postdoc, working at the Técnico de Lisbon. So today he will talk about the onset of scalarization in generalized scalar-tensor theories. So please, Antoine, go on. I will tell you a reminder when you have like 10 minutes left
Okay.
for the talk, and have a nice talk.
Okay. Thanks. Yeah. Thanks a lot for the invitation. Yeah. I just want to apologize in advance if my connection breaks down during the talk because it's been very unstable for the last week. So I hope this doesn't happen. But it might cut at any moment. So let's see. So yeah, I'm going to discuss a phenomenon that is called scalarization, and I will try to discuss it in a fairly generic setup. So this is based on a work that we did last year with Thomas Sotiriou in Nottingham University and Giulia Ventai, he's a PhD student. So first I will start by telling you in which framework I am working, these generalized scalar tensor theories. Then I will tell you a bit in more detail what scarization is. And then we will see the details of which operators contribute to this phenomenon. So first of all, I would like to start with motivating why we would like to modify our theory of gravity, because the scalarization is a modification of general relativity. So there are several classes of reason. First of all, there are some phenomena, some observations that we have and that cannot be accounted for by just GR plus the standard model of particle physics. So these include dark matter, inflation, dark energy, and many others actually, which I didn't list here. A second class of reasons for changing GR is that it intrinsically contains some limitations. Like we know that the theory is non-renormalizable, that it will produce singularities in the center of black holes or at the beginning of the universe. Some problems are also a bit mixed. So the fact that the cosmological constant is so small is related to dark energy, but these are all theoretical arguments that we need to treat. And finally, maybe the reason which motivates the most what we are studying here is that we have gained access to a new observation channel recently with gravitational waves through LIGO and Virgo detectors. So now we can test gravity and we can test different models from GR in a very strong field regime instead of just performing null tests of GR. So this is also interesting if it's just, even if it's just motivated by theoretical curiosity. So having said this, I'm going to discuss scalarization. So obviously it involves a scalar field. So it's a modification of GR with a scalar field. And we can wonder why modifying GR with a scalar field more than any other modification. So first, one argument for this is that it's it's a fairly successful and standard procedure when we want to go beyond the theory to add it a scalar field. Like that's what we did for inflation, quintessence, or actions with the strong CP problem. So it's fairly common and usually successful. It's simple. I mean, it's the simplest additional degree of freedom you can add, and this is probably the true reason why we are doing this. And finally, many other modifications of GR that you can think of, they are often related to scalar tensor theories, at least in some regime. Yeah, even from extra dimensional theories to Horta-Lifshitz or Einstein ether or even massive gravity, you often have a scalar mode that appears in these theories. So it has a lot of overlap with other models. Now, if we decide to modify gravity with a scalar field, we can wonder what is the most generic way of doing so. And this question was asked already by Horndeski in the 70s. So in detail, what he was asking is if I start from an action that contains a metric degree of freedom and an arbitrary number of its derivatives, and same a scalar field with its derivatives, what is the most general Lagrangian I can write, which has only second order field equation in the metric and in the scalar. And the reason for asking that it's only second order derivatives in this equation is that then you are sure that you avoid what is called an Ostrogradsky ghost, because generically, if your field equations contain higher than second order derivatives, if you do the Hamiltonian analysis of the theory, you will find that the Hamiltonian contains a term that is linear in some momentum, so it cannot be bounded from above or below, and this immediately creates an instability. Well, there are some exceptions to this that actually we are going to see that they are included in our study. So this is the answer to Horndeski's question. You don't have to read all the terms in this slide in detail. It's just to show you the framework in which I'm going to be working. But in fact, for scalarization, we are going to see that only some of these operators are relevant. So basically, it's parameterized by four functions, G2, G3, G4, G5. And yeah, as I was saying before, you can slightly extend this framework to what is called beyond Horndeski or dust theories or extended scalar tensor theories, which I mean the healthy theories among these ones can actually be obtained by taking Horndeski action and coupling matter to this modified metric G tilde, which is just G to which you applied a conformal transformation and what is called a disformal transformation parameterized by these two functions C and D. And yeah, what I'm going to present in the rest of the talk also covers these classes of models, in fact. So now, what is Scarization? So the idea dates back from the 90s. It was developed by Damour and Esposito Ferrez. And here is the idea. Basically, you've got a scalar degree of freedom, and its equation looks like this, at least the linearized equation. So you have box phi equals some effective mass, which depends on the metric, so on the curvature also, because it depends on its derivatives, times phi. And this effective mass is designed in such a way that in weak curvature regimes, for instance, in the solar system, it is positive. Then this equation tells you that basically phi equals 0 is a stable solution, and you can have GR plus a trivial scalar field. But then if you go to strong curvature, if you crank up the curvature enough in this effective mass squared, the effective mass squared becomes negative. And then this is a tachyonic instability, and the scalar field, it will start by growing exponentially, and ultimately this growth will be stopped by nonlinearities either in the metric or in the scalar field. But so it will, in any case, it will lead you to another branch of solutions with a non-trivial scalar field, which are no longer GR solutions. So yeah, in these kind of models, you expect modifications in strongly curved objects like black holes or neutron stars. Initially, it was designed for neutron stars. So then, yeah, you can ask, what is the most generic effective mass term that I can write here in the framework of Horndeski theory or its extensions. And this was answered actually by Nicolas Andreu, Nicola Franchini, who is there, Thomas Sotiriou, and Giulia Ventagli in a paper 2 years ago. So they listed all possible operators that can contribute to scalarization. So to its onset, in fact, because we want to know, I mean, if you want to scalarize some object, you have to first, I mean, it starts from a GR solution. So it starts from phi equals 0, and you have to list the terms that contribute linearly, because these are the ones which are going to determine if you get scalarized or not. So in this minimal action, I put the non-standard terms in blue. So you have just a Ricci scalar, of course, plus these d phi squared and m phi, phi squared are just the canonical scalar field. But then you also have other terms that contribute at linear order. So you have this kinetic coupling to the Einstein tensor. And so this will contribute actually to the effective metric in which the scalar field propagates. And then you have two terms, only two, that can contribute to the effective mass for the scalar field. So these are a coupling to the Ricci scalar, which was the original one. Well, actually, at least the original formulation of the Moore and Esposito-Fares was amounting to this coupling. And then you have another coupling that was discussed more recently. In fact, maybe 4 years ago, people realized that you could also have scalarization if you couple your scalar field to the Gauss-Bonnet scalar, which is written here. So it's just a quadratic quantity in the curvature. And so if you start from this minimal action, you obtain the following equation for the scalar. So as I said, it propagates not just in G mu nu, but in this effective metric G tilde, where G, the Einstein tensor, also enters. And yeah, it sees an effective mass, which is the bare mass plus the Ricci scalar coupling and the Gauss-Bonnet coupling. And so everything basically is parameterized by these three numbers, alpha, beta, and gamma. And in what comes next, I'm going to try to put some bounds on these parameters, or to see at least for which precise value of these parameters scalarization starts. So the technique then is the following. We consider, of course, I'm not considering the scalarized solution themselves. I just want to know when will scalarization start. So for this, we take a GR background, in this case, a neutron star that we take to be spherically symmetric and static. And we see when this star is going to scalarize or not. So thanks to spherical symmetry, we can decompose the scalar perturbation in spherical harmonics. And we focus on the L equals 0 mode, because this is the one that is that actually becomes unstable in first. And then we look for solutions of this form, which are going to grow exponentially with time. And so if we are able to find an omega for which this happens, that means that the solution is unstable. In fact, the previous scalar field equation here can be, if you rescale the scalar field and you change your radial coordinate, you can cast this equation in the form of simply a Schrodinger equation. And so then it simplifies the problem, because the only thing you have to do, in fact, is to look for the bound states of this potential. So as soon as you have a bound state, so a state with negative energy, here it's actually minus omega squared that plays the role of the energy in quantum mechanics. So when you have a bound state with negative energy, that means that you have a solution with real omega, so that your scalar field is going to grow. So that corresponds to an instability. So the idea is the following: you start from GR with all these, so these are the parameters that describe your deviation from GR. And so of course for alpha, beta, gamma equals 0, you just have GR, so your scalar field doesn't have any instability. And when you progressively crank up these parameters, either alpha, beta, or gamma, this might trigger an instability by deforming this potential and giving it a bound state. So that's what I'm going to describe in the following sections. So first, I'm going to follow on the terms that contribute to the effective mass. So that's the Ricci scalar coupling and the Gauss-Bonnet scalar coupling. So for now, I'm just switching off the terms that was parameterized with gamma. So I just have this effective mass beta times the Ricci coupling, the Ricci scalar, minus alpha times the Gauss-Bonnet scalar. And this is the kind of plots we are going to be looking at. So what does it show? Here we have taken a background for the background. We have taken a star with mass 1.12 solar masses. So this corresponds to a very light neutron star. In fact, we will change the mass later to see how this changes. And we took an equation of state that is SLY. We will also see what happens if we change the equation of state, but it's not very strongly dependent on the equation of state. So this is the kind of results we get. So you can read this plot, for instance, but on the horizontal axis, you've got beta, the coupling to the Ricci scalar, which is dimensionless, and on the vertical axis, you get alpha, the coupling to the Gauss-Bonnet, which is a length squared. So of course, if you are sitting at alpha and beta equals 0, you are in GR, so your solution is stable. And the meaning of this plot is that if, for instance, if I start increasing alpha and beta along this line, then I'm going to hit this first black line, which corresponds to the first bound state for the potential, and then therefore to the first instability for the scalar. And each of these lines actually corresponds to a new bound state. So as soon as you exceed the white region here, you are in an unstable configuration, and more unstable as you cross more and more lines. The lines are just labeled by so this number n here, which corresponds to the number of nodes of the scalar field solution. So just like in quantum mechanics, you can count the number of nodes of your eigenfunctions for the potential. And I'm going to leave this in the next slides. I'm going to leave this plot in small in this corner so that we can see what happens for comparison when we change either the mass of the star or the equation of state, or we put a bare mass. Yeah, final comment on this plot. You can notice that if you restrict, so yeah, basically actually what was known, because this is not entirely new, what was known was the restriction of this plot to the line beta equals 0 here and alpha equals 0 here. And now we instead of having just these two lines, we extended it to a 2D parameter space. And you can see, for instance, that if you restrict to alpha equals 0, so just the Ricci scalar coupling, you get scalarization only for negative values of beta. If you go to positive values, nothing happens. So we are going to see why. On the other hand, if you take a very negative or very positive alpha, you get scalarization. So you can, one way to understand this is to plot the things to which alpha and beta couple, so the Ricci scalar and the Gauss-Bonnet invariant. So we see that in this configuration for this star, the Ricci scalar is in fact always positive up to so this is the Ricci scalar as a function of the radius, 1 being the radius of the star, the surface of the star. So for this configuration, it's always positive. So of course, if you take beta positive and alpha equals 0, then your contribution to the effective mass squared is always positive. So it's not surprising that you are not going to trigger any instability. On the other hand, if you look at the Gauss-Bonnet invariant and you plot it again against the radius, there is a region towards the core of the star, it's positive, and in fact close to the surface and a bit out of the star, it's positive. So it changes sign, hence for both alpha positive and negative, you are going to trigger scalarization. Oops. We are going to see that actually this is not always the case. So you can have stars for which, in the case where the star is very compact, we will see that the Ricci scalar can become negative also towards the center of the star, and we will see how it manifests in these stability plots. So here in this plot, I'm just, again, I leave the previous one for comparison. So this is just the same plot when we added a bare mass to the scalar field, and a very light bare mass. As you can see here, we just took a mass of 1.33 times 10 to the minus 10 electron volt, still with the same equation of state and still with the same mass for the star. But you see basically the difference between this plot and this plot is that the white region is much, much larger. So in fact, the effect is that of adding a bare mass is that it stabilizes the solution very quickly. So even for these very light masses, and we choose this, we chose this mass just because it's the mass for which the scale at which things happen. But if you were to take a much larger mass for the electron volt, for instance, you wouldn't see anything on this plot. Everything would be white and everything would be shielded from scalarization. So a bare mass really tends to shield the compact objects from scalarization. Another thing you can change, so I'm back here to vanishing bare mass. Another thing you can change is the mass of the star that you are considering. So here we took the maximum mass we could reach with this equation of state in GR, so to around 2 solar masses. And again, this is we went from this plot for light neutron stars to this one. And so you can see that the most striking feature is that what was before a wedge in this alpha beta space turned it into an island, because the stability region closed on the side of positive beta. You can actually relate this, as I was saying, to the Ricci scalar, because now if I plot the Ricci scalar for this configuration, for this mass of the star, this is what it looks like. So it has a bit the same shape as the Gauss-Bonnet invariant, and you see that in some region it's negative, in some other region it's positive. So for both signs of the coupling to the Ricci scalar, you can actually have scalarization. So that's what you observe here. If you stick to the alpha equals 0 line for negative beta and positive beta, you will get scalarization in the two cases. Yeah, this was, again, the restriction of this to the line alpha equals 0 was already known and studied. I mean, it was already noticed by Damour and Esposito Fares in their original paper that for very compact stars, the pressure becomes very large, so it can become a 3p can become greater than the energy density, in which case the Gauss-Bonnet become not the Gauss-Bonnet, the Ricci scalar becomes negative to the center of the star. Right, and the last thing we can change the equation of state. So we tried to consider equation. This plot is not by us; it's just from LIGO and Virgo collaboration, and it's I think it's titled "Deformabilities from the Neutron Star Merger." This plot just shows that the only event we observed so far for neutron star mergers tends to prefer these soft equations of state, so corresponding to more compact stars. So before we were using the SLY equation of state. So if we now try the MPA one, this is what we get. And you can see actually that the difference between the original plot and this one is not very different. We kept the same mass for the star in these two configuration. We just changed the equation of state, so it's fairly independent on the equation of state. Right, that's it for the terms that contribute directly to the effective mass. Now I am going to discuss the ones that contribute to the effective metric. Unless you have questions. Yeah, sorry, I didn't say that, but of course, if you have any question, feel free to interrupt me. It's fine. So concerning the effective metric, as we said, it's affected by this gamma, this third coupling that I call gamma to the Einstein tensor. And actually, independently of scalarization, we are able to, thanks to our analysis, to put a bound on this parameter. And you can realize where the problem is by considering this effective metric for the scalar field. So it's G mu nu, the standard metric, minus gamma times the Einstein tensor. And since we are still on the GR background, you can use Einstein equations and you replace G mu nu by T mu nu, the stress energy tensor of your, here it's a perfect fluid for the neutron star. And here you can see that there is a problem because if you look at the signature of the tensor T mu nu, it's plus, it's only pluses, so it's plus, 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 plus. While this one has the right, the correct signature, so minus, plus, plus, plus if you want. And so that means that if you crank up too much the parameter gamma here, this is going to dominate, and you are this will have the signature of T mu nu, and you are actually losing the hyperbolicity for the metric of your scalar field perturbation, which is very bad. I mean, it's not the tachyonic instability, it's another instability, which is worst, in fact, gradient instability. And so, yeah, in fact, what in our philosophy, we just decided to exclude the models that were not respecting this hyperbolicity condition. Maybe actually you could consider that and this is a way to another way to scalarize, and this has not been studied, but that would be, yeah, it's interesting, and I don't know if it's possible actually to make sense to keep the growth of the scalar field under control or not, but this is also a possibility. So we in our analysis we just decided to exclude the models that do not respect the hyperbolicity for the scalar field. It's actually pretty easy to find the bound on gamma. You can, for instance, compute the determinant of this effective metric and for a perfect fluid, and you see that it changes sign for a critical value of the pressure and the density. So this restricts your gamma between well, the point where the density, the energy density is going to be maximal, that is the center of the star, and same with the pressure. So this gives you two bounds on the parameter gamma. Sorry, maybe I didn't say it. Kappa here is just 8 pi g over C4. And yeah, one of these bounds was actually already noticed in a paper, but they were, for some reason, they were not, yeah, they were, because they were already working in spherical symmetry, so they didn't realize this corresponded to hyperbolicity of the metric, so we get a second bound. Here, this plot is different in essence to all the ones I was showing you before. It's just showing what these this interval corresponds to in terms of the mass of the star. So from basically 1.1 to around 2 solar masses, you see that you get, I mean, gamma is restricted to be in this range. If it's outside of this range, you will also have a gradient instability. And so since we observe stars of mass around 2 solar masses, it seems fair to constrain gamma to be in this range. So this gives you the following bound on gamma, which also has units of length squared. So yeah, it's not it's just an order of magnitude on the bound because it depends on, then it depends on the equation of state you're using, for instance. But still, it's I think it's nice because this parameter is not really constrained otherwise. So this gives a constraint on this operator coupling to the kinetic coupling to the Einstein tensor. So now, if the final thing we can check is that if we restrict, we respect this bound, we still have some freedom on gamma. So how does it have any effect on the onset of scalarization? And the answer is no, in fact. So here you see gamma is on the vertical axis, and in this plot we are varying also the coupling beta to the Ricci scalar. In this one, the coupling to the Gauss-Bonnet scalar. And what is important actually is that the line of stability, the separation between the stable and the unstable region is almost vertical, because if gamma is restricted to these values, it's actually too small to have any effect. So basically, independently of the value of gamma, scalarization is always going to happen around beta equal -5 around here. And same for alpha, independently of the value of gamma, the scalarization always happens in the same band for alpha. So it's actually, I mean, this coupling is actually pretty irrelevant, although, I mean, we had to do this analysis to show it, but you can in fact ignore it if you want to know which models are going to scalarize or not. All right, this is what we did, and I would just like to finish with the prospects of like how we want to continue this study. So a very important aspect that well, actually we are studying it now is what this scalarization process leads you to. So because here we just looked at the stability of the GR solution and we are able to say when GR is stable or not. But then after you trigger the instability, you want to know where the solution is going. And for this, you need to include some non-linearities in your analysis, like they can just be non-linearities that are associated to the metric, because when the scalar field grows, it will back react in a nonlinear way on your metric. So this will change the geometry, and this might be already enough to stop the instability. Or if you want to be sure that your scalar field will not grow too far, you can just include some nonlinear terms, either in the potential, in the bare potential, or in the coupling functions to the Ricci scalar or Gauss-Bonnet scalar, like phi to the 4 term. So once we perform this analysis, we will be able more or less to plot the same maps we were doing before with alpha beta, but on top of the stability regions, we will be able to add the regions where scalarized solutions actually exist or not. And yeah, another interesting aspect of this is that we also want to probe the effect on the Ricci scalar coupling here on black holes scalarization, because it is often ignored. Indeed, it doesn't contribute because, you know, for GR solutions, they all have a vanishing Ricci scalar, so it's not contributing to the onset of scalarization. But as soon as you trigger scalarization with the Gauss-Bonnet invariant, then this term is going to be there, because the Ricci scalar, I mean, the solution is no longer Ricci flat. So in fact, you wouldn't even expect that as soon as you move out of the GR solution, this will dominate with respect to the Gauss-Bonnet coupling. So it's interesting to know its role in black holes scalarization. Yeah, another aspect, of course, is the stability of these scalarized solutions, because it's not because GR is unstable and that there exists a scalarized solution that is good. You still have to check that it's actually also stable. So this can be checked by a standard procedure of decomposing the perturbations. And even it's even possible to compute the quasi-normal modes associated with these with the black holes solutions, for instance. So there's pretty much some work to do. And ideally, what we would like to achieve is a model for which I mean to know in which regions of the parameter space you can have scalarization switched on only for black holes, because the thing is that for neutron stars, it's been studied for a while, and there are pretty strong constraints on a neutron star. Basically, the pulsars constraints tell you that pulsars are not scalarized. So it would be great to have a model for which neutron stars are not scalarized, for which also you have a cosmological history that is fine, because what happens, for instance, to the original Damour-Esposito-Fares model is that in cosmology, if you take the sign that you are interested in for a neutron star, it will also scalarize cosmology, which is very bad because you don't want the whole universe to be scalarized. So the goal is to achieve non-scalarized neutron stars, non-scalarized cosmology, but scalarized black holes. Just to give you an idea, that would correspond basically. So this is still the map with the coupling to Gauss-Bonnet and Ricci scalar. So we want to be first in the region, in the white region, so that neutron stars are not scalarized. Then we want to be in the region which is fine for cosmology, so that corresponds basically to positive beta. And finally, we would like black holes to scalarize, which corresponds at least for spherically symmetric black holes, because then you might also have for the other sign, you might have, if they rotate, you might also trigger scalarization. But if they are spherically symmetric, this will be in this region. So basically, we think that in this region here, that is the overlap of the white, blue, and red, you might fulfill all the criterions that all the criteria that we would like to fulfill. And okay, that's it. I'm just giving you a recap of what we achieved. So all the terms that contribute to scalarization had been listed before, and we computed the exact thresholds for which you have onset of scalarization. And we saw that we computed the exact onset threshold for these two parameters, and we saw that the last coupling, the last operator that can a priori matters in the onset of scalarization, has in fact no significant effect. Yeah, that's it. Thank you for your attention.
Thanks, Antoine, for the very nice talk. So you've been very fast. I even didn't tell you the
Yeah,
time.
sorry.
So no, but it's good. So we have some time for questions. So if you want to ask a question, you can just unmute yourself and ask, or raise your hand.
Maybe I can ask a question.
Yes.
Yeah. Well, first of all, thanks for the nice talk. So when you say constraints from cosmology, you mean background cosmology and the fact that the scalar field doesn't settle to a minimum at late times. I
Yes.
imagine. Did you look into constraints from the coincident detection of the by LIGO and Fermi of the? Is there any constraint that you can place using the speed of gravitational waves on this?
Well, so in this, I mean, yeah, there are two separate aspects. So yeah, first of all, I want to say that where is it? This operator here, the coupling to the Einstein tensor, it is constrained from precisely this what you say, the speed of gravitational waves, actually much more constrained than this in this framework. But that is if you assume that your scalar field is playing the role of dark energy, which we do not assume here. And then to answer the other aspect of your question, There was a paper by Thomas Sotiriou and his PhD student Georges Antoine and Lorenzo Bordin, where they were computing. I mean, they were working in the framework of the coupling to the Ricci scalar and the Gauss-Bonnet with just the quadratic coupling to phi. And they were showing that it's possible to have a consistent cosmological history in which the scalar field, like the density of the scalar field is negligible at late times. So then in this framework,
sorry, this is for positive beta, right? For the sign.
Yeah, this is what they were obtaining is basically, yeah, because basically the thing is that the term with the coupling to the Gauss-Bonnet is important only at early times. Then it decays very fast because the curvature becomes much.
I'm confused about why the Gauss-Bonnet term is actually important, because I thought the Gauss-Bonnet term is a topological invariant, and the topology of a Robertson-Walker metric is the same as Minkowski space, which has no holes. So I thought Gauss-Bonnet was zero for the
well
flat cosmological background.
No, it's not zero. It's well, the thing is that it's a
because the Gauss-Bonnet, isn't it the number? I mean, it's a topological invariant.
Yeah, but I think that is if you work in a purely gravitational theory, and if you start coupling it with the scalar field, it's no longer a topological invariant. Because, or actually, well, maybe it's the overall. If you integrate the Gauss-Bonnet over your
I think so is it, correct me, maybe I'm wrong, but I thought if I just evaluate the Gauss-Bonnet, just the invariant on Robertson-Walker, don't I get zero?
Well,
maybe I'm wrong.
No, on Roberts. No. I mean, I sorry, I don't have the expression here, but you can find it in this paper. I'm sure it's not zero.
Okay.
Yeah, and also because yeah, it depends. Like for instance, in these plots, clearly it depends on the location. So I think it's only the integrated quantity over the whole space-time that is invariant.
I see.
Then it depends on
yeah, that's right. So it's the integral of the.
Yeah. So maybe
the number of
the integral in FLW is zero. That might be true.
Thanks. That answers my question.
Are there further questions?
I would have another question, but it's just a request for a tiny clarification because maybe I missed a detail. Regarding the effect of the gamma parameter, so the modification of the metric,
yes,
or the effective metric for the scalar. I didn't quite understand whether this modification is enough to give a scalarization on its own, or you just included it to see how can it modify the onset of the scalarization.
Yeah. So yeah, the answer is no. It's not enough to, because if you go back to this equation, in principle, what is triggering scalarization is this negative tachyonic mass. So if you just have gamma on its own, it's not going to be enough to trigger scalarization. But the thing is that if you want to analyze consistently all terms that contribute to the linear order in the field equation, you need to include it a priori. So yeah, it's not enough to trigger scalarization by itself, but in principle it can play a role. Actually, we saw that it's not playing much role, but a priori it could have. Yeah, actually the last thing is, as I was saying, that you could have another type of scalarization, which is based, instead of tachyonic instability, on gradient instability. Like if you lose the hyperbolicity here, this triggers the growth of the scalar field that might also be quenched by nonlinearities. But I honestly have no idea if this is viable, or if you can control the growth of the instability, especially at higher frequencies. I'm not sure this is a healthy procedure.
I see. Then maybe can I ask another quick second
Yeah.
question? Um, so as I see, you of course studied the scalarization as triggered by curvature effects, right? So you
Yes,
considered the couplings to curvature or curvature squared that could affect the mass of the scalar field at linear level.
that's right.
Um, I don't know if it's if it has any meaning, if it's interesting at all, but what about considering also a conformal coupling to matter? That is it even interesting? Is it even
Um,
because in that case, that's the
yeah,
classical Damour Esposito Farese
yeah, yeah, yeah,
scalarization, right?
yeah. No, in fact, this is. I think this is not bringing anything new with respect to. Sorry, where is it? To our analysis, because again, this is just the terms that matter for the onset. So if you um, the thing is that I mean, I actually you studied that in a paper, Nicola. But if you instead of putting g here, you put the g tilde that was here, so a conformal plus this formal transformation at linearized level. This is the same. I mean, this you can recast, you can change your variables, and this is the action you're going to end up with. So at the terms that contribute for the onset of the scalarization, they are only these ones, even if you include the conformal or disformal couplings here.
I see. So with another conformal transformation, you can recast
Yeah,
the action to be essentially
yeah,
equivalent to this one. I
yeah,
see. So essentially, the Damour Esposito Farese like scalarization has triggered to from the coupling to matter. Maybe it's a mixture of these terms.
yeah. I mean, it's this for the onset plus other terms that come like when the scalar field starts growing. Then you take into account the nonlinearities, and then
Sure,
of
sure,
course
sure.
you cannot all reduce to this, and it actually then it becomes different if you put the terms here directly in the gravitational action or in as a coupling to the matter here.
Okay, thank you.
Okay, if there aren't any more questions, I actually have a question, Antoine.
Mm.
So it's about the bound you're putting on gamma.
Mm-hmm.
So the thing is, like, you're putting this bound considering that your background is a spherically symmetric and static solution.
Right. Yeah. Yeah. Yeah.
So,
Yeah.
but so this is in principle. I mean, you're asking for hyperbolicity, but hyperbolicity comes when you're doing an evolution over time, and then the structure of G is gonna change in that case, right?
Yeah, but still, the thing is that, I mean, that could only strengthen this bound, I guess, because here I'm just saying that if I take a spherically symmetric neutron star and I put a scalar field on top of that with an operator that doesn't satisfy this bound, then it's going to start to grow and behave super weirdly. So
Yeah. Oh, no, of course. But I mean, yeah, that could be a way to.
yeah, no, yeah, this is just yeah, I mean, it's just an order of magnitude because again, it depends. It depends. I mean, yeah, a spherically symmetric neutron star is not a realistic background. It depends on the equation of state, but just in principle, there is this bound.
Mhm. Oh, yeah, okay. Miguel
Sorry,
has a question.
Miguel,
So
no.
his computer broke.
So regarding the hyperbolicity,
Yeah.
just a curiosity, how did you study them with this effective metric? How did you put the
Uh, well, I'm just saying that because the thing is that it's pretty simple in the case of a perfect fluid. Here, I can just replace T mu nu by its expression, and then it's pretty easy to see. I mean, it's just that the some also I can write it in spherical symmetry, and I can see which components are going to flip sign or not. So it's just then I say that the determinant of the metric is this, and I know that if this changes sign, this will correspond to a change of sign in the metric, and it will lose hyperbolicity then.
Okay,
Yeah.
perfect.
Then, yeah, indeed, on a generic background, which is not a perfect fluid, not in spherical symmetry, I don't know how easy it is to decide if this is hyperbolic or not.
Okay. And do you know if there is anyone doing evolution of this or someone?
No, I don't think. No, because even at the even at the theoretical level, as I was saying, I don't know if it would be interesting to decide if this can lead to scalarization or if this is just a sick theory that is going to blow up in the ultraviolet. I don't know, but I don't think anybody has studied that.
Okay. Thanks, Antoine.
Enrico is saying William Inst knows. No, it was he gave a seminar here last week
Okay.
about evolving binaries in Hordenski theories.
Okay. Well, that's hard.
Okay, so I think
Actually,
is there another question?
yes.
Yes.
Hello, Antoine. I have a question about cosmological relevance for this model. So, for example, if you
Sorry, I didn't
consider,
hear.
yeah, do you hear me?
Yes, I hear you now.
Yeah. So I'm talking about cosmological relevance of this model.
Yeah.
For example, if we want to interpret this scalar field as dark energy, how we can explain, for example, boundary condition on, for example, for this model in black holes, we consider only asymptotically flat black holes.
We cannot understand very well the question.
Yeah, I'm sorry, I understand.
Okay, I will just remove the phone.
Because I think your microphone is.
Can you hear me now?
Yeah. So you said, sorry, you said if the scalar field is not playing the role of dark energy.
Yeah, is it better?
Yeah, go ahead.
Yeah. So I said if we want to consider this scalar field as dark energy, we consider a model, for example, the one by Silva, Soterio, and Gualtieri, and so on. So they consider asymptotically flat black holes. So condition on the boundary, we have the scalar field, which is zero. So how we can interpret it as dark energy? This is the first question. And the second one, if, for example, we consider the model of Damour, Esposito Fares, or even this model from Schoenstatt and so on, to have an interpretation in cosmology, we need a fine tuning, but this is not nice, for example, for inflation, because we will have like instabilities due to quantum corrections and so on.
Okay, so to answer the first point, precisely, we don't want it to play the role of dark energy because I mean, yeah, it's just not the purpose is to describe modifications of gravity in strong field regimes, and this is consistent actually. You can show. I mean, there are some papers by for instance Nicola and Thomas Sotirio where you can show that this scalar field can be just trivial at cosmological level. So in this condition, it's fine to assume that it's asymptotic C0. On the other hand, there are also some solutions where people have studied it, like my PhD advisor, Christos Charmoussis. That's one of the things he was doing, taking time-dependent ansatz for the scalar field and matching it with, for instance, with the Sitter asymptotics. You can do that, but it depends on what you want to do, and it's up to you. You can treat the scalar field as dark energy or not. And then what was the second question about fine-tuning of which parameters?
For example, for the model of Damour Esposito and the other one,
yeah,
the problem is inflation because there will be instability due to quantum.
Oh yeah. There is well, yeah. So for fine-tuning, I'm not sure because, for instance, well, it depends on the couplings to matter because if it's only coupled, if your scalar is only in the gravitational sector, I'm not sure you will have huge renormalization from the matter sector. I'm not sure this is inconsistent. Then yeah, indeed that's true. You're right. There is a problem with these models for inflation. So when I was saying in the end that we want a consistent cosmological history, that's at least up to the end of inflation. Then before that, that's true that these models are not satisfactory. Although there are also some works, but then you need to do intricate these plannings might work, but it's not yet clear. That's true.
Okay, thank you. So you mentioned the work of Christos. So did they find rare black holes in those, but which are cosmologically relevant?
Yeah. I mean, then it's actually one argument. Like if you say this scalar field that I'm using is describing cosmology, then in fact I should have some hair because it's just what my asymptotic condition dictates. So they have some hairy black hole solutions that at least can be regular at the black hole horizon. So yeah, there is several of these solutions. Yeah.
Okay, thank you very much.
Okay, thanks again, Antoine, and thanks everyone for being here. I've